We will see today how to calculate the sample size for measuring correlation between pairs of variables or agreement between pairs of variables. And we will divide this, we will see a number of situations. The first one, and we will divide them in two groups. The first group is related to the standard Pearson correlation coefficient. So we will learn how to compute sample size when you are studying the Pearson correlation coefficient. The other ones are other ways of measuring the association between variables, and then these are more specialized cases, and then we will see them in a separate video. So let's start with the first group. So in the first group we are studying whether there is a correlation between a given hormone, that is aldosterone, and blood pressure. So we will study the concentration of this hormone in blood and compare it to blood pressure. So for a number of people, we will measure this X, that is the aldosterone concentration in blood plasma, and we will measure a variable Y, that is the blood pressure, and then we will compute the correlation between X and Y. We expect this correlation to be around 0.25. How many individuals do we need to study if we want to construct a confidence interval with a lower and upper bound on this correlation? This correlation coefficient, you know that it goes from -1 to 1. -1 meaning a perfect inverse linear correlation or relationship, and rho equal 1 is a perfect linear correlation, linear relationship between the two. So 0.25 is not too high, so it is a relatively weak correlation between the two. Okay, so we want to construct this confidence interval with a precision of 0.05, and we want to have a confidence level for this confidence interval of 95%. As we have done in other cases, we will look for a Gaussian distributed variable, and then we will compute the sample size under that approximation. So the distribution of rho, the correlation of the correlation index, is skewed, but the Fisher's set transform is approximately Gaussian. This is the so it is the hyperbolic tangent arc of this, and it is also can be calculated like this. Okay, and the good thing is that the variance of this transformation is 1 over n minus 3. Okay, so then we can try to look for the lower and upper bounds, such that rho has to be here with probability 1 minus alpha, and we can translate this interval in rho into an interval in the set transform variable, and then we would have here we would have what is the lower bound, what is the upper bound, and these lower and upper bounds in the set transform domain, it is symmetrical. So this is this one minus a given amount, and this one that is the same, that is the central value, plus the same given amount, and then from there you can solve for n, and n is equal this, and we recognize the typical confidence or the typical sample sizes for confidence intervals in Gaussian variables, that is the term on the confidence level and then the normalized effect. Okay, so substituting our values, we have this, and then delta z, that is the difference between the upper and lower bounds are these ones, and then n is 1300 or 1400 almost. And it is important to make a clarification, as we have always done with the sample size calculation. We need to hypothesize to what is the expected value. It doesn't mean that the true values will be exactly the ones that we have chosen. They don't need to be this 0.25. So, but it has to be around, because otherwise we cannot make any calculation at all, and we cannot know what are the values that the sample size that we need to have more or less that precision. So you see, we have 0.25 minus our precision, 0.25 plus our precision. So it doesn't mean that we have to know exactly before doing the experiment what the values will be, but we need to have some ballpark values. Okay, what about the test for a correlation when we have only one sample? Okay, so we suspect that the correlation between the height and the weight of a person is smaller than 0.9. So how many individuals do we need to inspect to show that the correlation is smaller than 0.9, and we want to have a statistical power of 90% if the correlation is 0.8 or below? Okay, so we extend the previous formula by including the statistical power in the formula, and then we simply have to apply our we see that here it is the delta set, so we simply have to substitute our values. So the lower and upper bounds are these ones, and then this is delta set, and then we simply calculate, and n is equal 65. What if we have two samples? So let's say that the correlation between height and weight in the general population is about 0.8, but we wonder if that correlation holds among some kind of patients, in this case diabetes type 2. So maybe in these patients the relationship between height and weight is somehow distorted, and so we wonder if in these kind of patients the correlation is smaller than in the general population, and we want to have a power of 90% if it drops below 0.7. Okay, so we define delta set as the difference between the two correlations. There is some mistake here, so this should be smaller or equal. It has to be the complement of this, and then the variance of delta set is this one. If the two group sizes are the same, well, then we can simply express it in this way, and then we can calculate the sample size in this way. So in this example, between of the general population having 0.8 of correlation, the diabetes having 0.7 or less, this is delta set, and then we simply substitute and get n equals 300. So we need about 300 people or more to have this precision. So this would be all for the most simple cases related to the Pearson correlation coefficient, and then in the next video we will see more examples about calculating relationship between variables, but they are more specialized ones.